One way of computing the determinant of a matrix that's particularly efficient if that matrix happens to have a lot of zeros in it is the method called cofactor expansion. Let's take a look at how cofactor expansion works. To calculate the determinant of this 4x4 matrix using the cofactor expansion strategy, the first thing that I'll do is write down what's called the Sine Matrix. The Sine Matrix is a matrix of the same dimension as the matrix we're trying to find the determinant of, but which stores an alternating sequence of plus signs and minus signs that's going to help us do a computation in just a minute. To write down the Sine Matrix, begin by putting a plus sign in the upper left entry, first row, first column, and then fill out the rest of the matrix with alternating signs. Just make sure that no two adjacent signs in this matrix are the same. They should alternate positive with negative. Once this Sine Matrix is written down, look at your matrix and select either a row or a column out of that matrix. And this strategy is the most efficient if that row or that column is a row or column that has a lot of zeros in it. So in this particular matrix, probably the most efficient choice for the row or column to use would be column 3, in which 3 of the entries in that column are 0, and there's only one which is not. So what we'll say is that we're going to expand this determinant into its cofactor expansion along the third column. Now, for each entry in the column or row that you selected, form a product of the sign of the corresponding entry in the Sine Matrix, multiplied by the entry from the matrix itself, multiplied by the determinant of what we'll call the minor matrix associated with that entry. Here's what that looks like. The first entry at the top of my third column is this one right here. In the Sine Matrix, that entry is a plus, so I'll write down a plus sign. I'm then going to multiply that plus sign by the corresponding entry from my matrix, which in this example is a 0, and multiply that by the determinant of the minor, which is determined by this entry. To find the minor associated with an entry in the matrix, all we need to do is cross out all of the entries that are on the same row as that entry and all of the entries that are on the same column as that entry, and take as our minor matrix all of the entries which remain. My original matrix in this example was 4x4. That means that all of the minors that are determined in this process are 3x3. And that observation is the key to why cofactor expansion actually works. It replaces every n by n determinant with a sum of n minus 1 by n minus 1, determinants which are one row and column smaller, and we hope easier to compute. In this example, the minor that we obtain is this 3x3 matrix, and that completes the entry that's corresponding to that entry in the third column that I'm expanding along. Now we'll repeat the process, taking the second entry in the column that I'm expanding along and multiplying its sign from the Sine Matrix times the entry from my matrix times the determinant of the associated minor. And in this case, there's the associated minor. Do it with the third entry, do it with the fourth entry. And at the end of this process, we've expanded a 4x4 determinant into a sum of 4 3x3 determinants, multiplied by entries from the corresponding column, multiplied by the signs from the corresponding column in the Sine Matrix. And it would appear that this is a more challenging problem than the one we started with. But we chose a column that had a lot of zeros in it, and so all of those entries that corresponded to the zeros in this expansion are going to cancel. 0 multiplied by the determinant of the minor just becoming 0. And therefore, in this example, we've reduced our 4x4 determinant problem down to what turns out to be a single 3x3 determinant problem. And then you ask, how do you compute that 3x3 determinant? We can do so in the same way, if we choose. Just repeat steps 1 through 3 for the determinant of this 3x3 matrix. Write down the 3x3 Sine Matrix, again starting with a plus in the first row, first column, and alternating signs along every row and column. Selecting a column of this matrix that has as many zeros as possible, or a row if you like, For illustration purposes, let's choose the third row of this matrix. It's got a 0 in it. And then, again, walking along that row, multiplying the sign from the sign matrix times the entry from the matrix times the determinant of the associated minor. The first entry will be a plus times a 1 times the determinant of that 2 by 2 minor, 1, 1, 2, 1. The second entry will be a minus times a 3 times the determinant of that minor. And the last will be a plus times a 0 times the determinant of the last remaining minor. And so now we've expressed this 3 by 3 determinant as a sum of 3 2 by 2 determinants. One of them happened to have a 0 as one of the factors, so that one can just cancel away. And we're left now with a sum of 2 2 by 2 determinants to compute. And 2 by 2 determinants are straightforward to compute in the first place, and this is why this process is promising. We can compute each 2 by 2 determinant by multiplying the diagonal entries minus the product of the anti-diagonal entries. So for 1, 1, 2, 1, we get 1 times 1 minus 1 times 2, or negative 1. And for minus 2, 1, 1, 1, we get negative 2 times 1 minus 1 times 1, which is negative 3. And since we know what those 2 by 2 determinants are, we then know that the determinant of my 3 by 3 is 1 times the first of them plus negative 3 times the second of them, and that comes out to 8. Therefore, the determinant of this 3 by 3 is equal to 8, and putting that back into context, the determinant of this 4 by 4 was equal to plus times 1 times that number. And so therefore, the determinant of this 4 by 4 matrix is 8. Now, the cofactor expansion method for determinants is not always the most efficient choice for taking the determinant of a matrix, especially if the matrix is very large. You might want to use row operation strategy instead. But in matrices that have a lot of zeros in them, this can be a very efficient way to reduce a large determinant down into a sum of smaller determinants. All you need to do is expand out along a row or a column by multiplying the associated sign multiplied by the entry multiplied by the determinant of the minor matrix, which is one dimension smaller, that each of those entries determines.